Alright, this is our lecture number 4 of business statistics. Just a quick reminder, so in the previous lecture we discussed how can we take data which is categorical. So in our case it was distribution of, well, not distribution, collection of responses, 252 if I remember correctly, from the graduates, and each response was about where did you find employment after graduation from the School of Business. So the possible answers were accounting, finance, management, marketing, and if none of these areas, then it's other. And how can we take this data, which is categorical, nominal, more specifically, and represented in form of a picture? So we discussed one of the most popular ways to do that, that's called bar chart. And we did that in R using the function bar plot. So in this lecture we're going to turn our attention to the next graphical technique that applies to numerical data actually. So for numerical data we're actually going to look at several of them. So the very first one that we will discuss in this lecture is going to be a histogram. Histogram probably hands down the most popular way to represent one single numerical variable. The representation of the numerical data is challenging. So why is that challenging? Here is the reason. Let me go back and discuss that. No, it should be somewhere. Can't remember on which slide I have it. Okay, well, let me just say it. The difference between numerical data and our previous data set that we looked at is pretty big. In the data set about the employment, this one, the only possible responses in my file could be 1, 2, 3, 4, 5, accounting, finance, management, marketing, or other. There was nothing else. So I could create very nice looking summary because there are only 5 possibilities. In example, when we have numerical data such as this one, phone bills, okay, I'm gonna tell you in a minute what all of that means. The numbers that we encounter in our data set can be really anything, and there is a pretty good chance that all the numbers in my data set are different from each other. So therefore that represents a challenge. So with employment areas I could have only 5 different possibilities. Here I literally may have infinite number of possibilities. And how do I represent something like this? So let's actually turn our attention to practice, so to speak. So the data set which is posted on the blackboard is phone bills. So let's kind of read a little bit about what exactly is that data set. So after phone industry deregulation, several new private companies were created to compete in the long distance phone services. So it probably refers back to the times when, you know, all these companies were created: AT&T, Bell South, Cox, etc., right? So since, well, phone company is phone company, right? What kind of service are you getting from them? Well, you pick up the phone, you dial the number, somebody picks up on the other end, you talk, that's it. So service essentially is the same, right? It's delivering the voice over the wire. So therefore, in order to differentiate yourself from other competitors, long distance company, the only thing that they can do is compete on the price that they offer to their customers. So to find out if there is an opportunity to gain customers by stealing from the competitors, a long distance company conducted a survey of its current subscribers and asked them, how much money was your last month's phone bill? So here is our assignment for this data set. Analyze the data graphically. Plot the data histogram, that's what it means. And then change the histogram for a class width to be $15. I don't know what that means, we'll see. And what kind of information can we extract from the data? So, well, let's go ahead and take a look at the data set, okay? So at that point you probably should go to Scholar. Here is a link to our course, Applied Data Statistics. and in the folder datasets I have posted the file right after the employment that we analyzed before, phonebills.csv. CSV is again comma separated value file, right? That's how we're going to save the majority, all of our data for this class. So go ahead and download that. And again, we're not using Internet Explorer, right? I'm using Chrome, and so probably should you, if of course you're running on the Windows PC. Okay, so now I'm gonna look in the downloads folder. So I'm gonna open up the folder with downloads right here, cut the file, and go to the data. Whoops. Oh, come on. Alright. Go to my folder data in the drive C and paste the file. So I'm moving the file with phone bills. And here in the preview actually I can see that there is only one column, right? And this column is called bills. But that's beside the point. Let me go ahead and bring up our tool. And the tool is of course our studio. That's what we're using. So since this is essentially the continuation of my previous lecture, right? We're still discussing graphical techniques to represent the data. I'm just going to continue the code, and at the end of this lecture I'm going to post that code in form of the .r file. So it's going to be an R script, right? In lecture notes right under the lecture. So actually, you know what, let me go ahead and make a comment right at the top. So first thing that we did is we created a bar plot, right? Bar plot for categorical data. So the employment data that we used is categorical, right? Accounting, finance, management, marketing are categories, they're not numbers, okay? And this is where we stopped, so I'm going to put a whole bunch of pound signs here to separate my bar plot. And let me start a new section right here. So here we're going to plot histogram for numerical data. Okay, so this script will consist of two parts. Okay, well, first things first, right? Before we analyze the data in any way or form, we have to read it from the file. So I'm gonna leave the comment here. Read phone bills data from CSV file. Excellent. So I'm going to call this. So the result of that is going to be data frame, right? A variable which has columns. Well, in my case, it's going to be only one column and bunch of records. Each record for every individual customer separately, right? So, but nevertheless, it's going to be a data frame. So I'm going to call my data frame phone bills data. And again, I'm using underscores in order to fill the gaps between the words, right, and have them visually separated, but yet at the same time, this is the name of my variable, so it should stay together. So no spaces are allowed, right? And I have to call the function read CSV, right? Here, if you remember, I can do it in a couple of ways, right? I can say file equal and then specify the full path to the file, or I can just skip file equal because by default it's going to assume that that's how it can find the file. So file is located on my drive C, the folder data, and it's called phone bills, I believe. Well, let's try it, right? If it's not called phone bills, it will tell me. So phone bills, when I run this line, I don't see any red stuff in my console right here at the bottom. That means that it did find the file and everything is fine. Okay, so let's do the same thing. Explore, right? Explore structure of the of data. So that is done by calling function str, and here I have to specify the name of my data. That would be phone underscore, and as I start typing I see phone bills underscore data, right? So I hit tab to select that, and then Control Enter to run this line. So here is the structure of my file. At the bottom, it has 200 observations. Okay, one variable, that means only one column, right? And the column is called bills, and it consists of numbers, you can see. And how do I know that? Well, here is my my clue, right? Numerical data. By the way, another way how I can find number of records in the data set is this. So I can, well, way number one is I can just simply run the structure, right? Function structure, that'll just tell me. But if for some reason I need to remember the number of observations in some variable for later use, here's how I can find it. Okay, so I'm going to leave the comment here saying find number of records, which, by the way, I'm going to call sample size, right? How many? So this is a sample. That's not everything, right? These 200 customers is not all the entire set of customers that the phone company has. So this is just a sample. So sample size, and let me call it n, just one letter. Okay, n is n row, and that's the function. N row of phone underscore bills underscore data. So when I run this, you can see right here I created a new value, right? N equals 200, and if I type it out, so I'm just gonna say, hey, show me what's inside the variable n. It'll tell me n is equal to 200. So this is this way I have number of records recorded and memorized in my memory, right? And the variable that holds the number of records for me is called n. That might be useful. Well, it's not going to be useful for our purpose right here immediately today in this lecture, but generally that might be useful for data applications. So that's just a side note. Okay. All right. So let's go ahead and create histogram. Simple as that, right? So I'm just going to create histogram first and then explain what any of that means, right? So here I'm going to leave the comment. Plot a histogram of well, my phone bills data. Okay. Well, strictly speaking, it's not the entire data, it's just one column inside the data, right? But yeah. Okay, so histogram is created in R using the built-in function HIST, and you can see as I start typing the name of the function, the help, dynamic help, shows up and it says, yep, histogram, I certainly know what you mean, my friend. Okay, and the only thing, I mean, I can just send a bunch of numbers to the function histogram, and that would be enough by itself. So, but we will see how we can change things a little bit to make histogram to look more presentable. So therefore, what I have to do is tell the program, tell R, what data do I want to plot? Well, my data is phone bills data, right? But I need to plot specifically a column, certain column inside of my data, right? And you remember how we reference specific column inside the data set, right? We have to specify the name of the data set. In my case, it's phone bills data with underscores. Then we have to say $, and then it will show the list of all columns in my data set. In this case, it's only one. Okay. And when I run this line, here's my histogram. Okay. So let's discuss what is that. Okay. So as we talked about the difficulty, the issue with representation of numerical data in one single picture, I kind of told you that with categorical data you have only a fixed number of categories and that's it, right? With numerical data you can see that my bills, right, are ranging apparently anywhere from close to 0 all the way up to about $120 apparently per month, right? So there are 200 numbers which are somewhere between 0 and 120, and there is a really good chance that the numbers do not duplicate, so every single bill is different. Okay, so I have 200 different numbers. So how do I plot that as a picture? So the idea behind histogram is this. We're going to split the entire range from 0 to 120, as you can see, in equal intervals. So there are two intervals right here, so that means that one interval is $10, right? So the first one goes from 0 to 10. The next one is from 10 to 20, 20, 30, 30, 40, etc., etc. And the last one is from 110 to 120. And what happens after that is, for each of these intervals, sometimes they're also called bins, we're going to count in the entire data set how many observations fall in the bin number 1. So in other words, how many bills I have between 0 and $10 a month. And what it looks like to me is I have about 52 or something bills, right? It's kind of hard to tell. The next one is all the bills between $10 to $20 a month. So it looks to me that I have either 32 or 33 of them, right? Essentially what I'm doing is, for each bill, I'm finding out in which of these buckets or bins that bill belongs. So if I look at every one of them, so first one, for example, right? There are 52 or so bills between 0 to 10. That picture doesn't tell me where exact numerical values of these bills are, right? Maybe all of them are close to 0, right? Maybe all of them are close to 10. Maybe they're kind of uniformly distributed between 0 and 10. That picture doesn't tell me anything. All it says is there are 52 bills from 0 to 10. That's it, the count, okay? So essentially what I'm doing is, now I'm representing my numerical data as just a bunch of categories, right? So my categories correspond to these buckets from 0 to 10, 10, 20, 20, 30, etc. So what histogram does is, out of numerical data, it creates categorical, well, more precisely ordinal data, right? Because my buckets or bins, they're ordered, right? This is a lower bin from 0 to 10 compared to the next one from 10 to 20, right? So there is order between the bins. But other than that, what I did is I took the numerical data and kind of created categorical data, ordinal, out of that. So essentially, I'm dumbing it down, right? So out of numerical highly privileged data, I created somewhat underprivileged data set, which is categorical. Right? So I'm losing a little bit of visibility, right? I don't know where exact numerical bill values are located, right? It's all kind of a little bit of the blur at that point, okay? But the advantage that I'm gaining is, now I can see where the majority of bills are distributed, where I have gaps, etc., etc., right? Okay, so that's histogram. All right, so let's beautify it a little bit. First of all, title kind of sucks, right? Histogram of phone bills, data, blah, blah. Okay, that one is also sort of not presentable. Frequency is okay, I'm guessing. Okay, so how do we beautify it? Exactly same way what we did for bar plot, right? So if I want the main title to look different, all I have to do is, just like I did for the bar plot, specify the main, right? Main equals quotations, don't forget them because it's a text, right? So this is histogram, or should I say distribution of phone bills. All right. Then I'm not going to change Y label, but I want to change the X label, right? So what do I do? X lab, right? Stands for X label, and again, quote unquote. How should I title that? Bill dollar amount. Bill dollar amount. Okay. I can give it a color, right? And it's exactly the same way as what I did here. Color right there. So COL equals let me gray. Make it gray. Okay, so let's go ahead and run this. Okay, and you can see that my X label has changed, my main title has changed, and now I have the bars colored gray. All right, now you remember the trick that we did with horizontal versus vertical appearance. Let's experiment and see if that still applies here now. Okay, so as I type horizontal, yeah, no matches. Okay, so apparently histogram does not support this function. HIST does not support being horizontal versus vertical, so that's the only thing that you can get. But I do know that remember how I was guessing that this is 52 and guessing that this is 33 or whatever it is. I can actually put labels on the top of my columns. Okay, so let's go ahead and do that. Labels equals, and this is actually a logical or boolean parameter, so it can be either true or false. So if I say labels is true, then labels show up. Okay, so you can see that the this was actually 52. Now it looks like it's cutting off a little bit. I'm wondering if I can expand the scale of this of the vertical axis in order for that to not cut off my at the top of 52. So we'll explore it in just 1 second. Okay, so this is 33, etc., etc. So now quite honestly, quite frankly, I wasn't prepared to do that, so we'll see if I will be able to find out the way how I can get it. So since I don't know all the bells and whistles for the function HIST, I have to find out, right? And you remember we did that for the function bar plot, so I'm going to do exactly the same thing here. I'm going to say, hey, can you show me function HIST and all the possibilities, endless possibilities that it gives me. Okay, so I'm looking at apparently this one, I'm guessing, x limit and y limit, the range of x and y values. Maybe it's this one. So okay, so let's see, x lim, is there an example? X lim range, alright, and y lim. Okay, so I'll try to I'll try my best in order to find out how that works. Okay, so y lim equals let me try just saying y lim equals 60. Will that work? No, it will not work. Okay, so range, let's try range. Okay, range from 0, let's say from 0 to 60. Will that work? Haha. Well, look at that. I'm so proud of myself. Okay, so you see what I did? I expanded the how tall my my y-axis is. So it was going up to 50, and now it goes from 0 to 60, and now it's not cutting off any of my labels. All right, so I'm going to go ahead and split it between the two lines. Let's see, right here. Okay. All right, and that's essentially how I can plot the histogram and manipulate how it looks. But one more thing that I wanted to show you is this: the way how the R broke down the entire range of 120 into the sub ranges, into these bins. It kind of took the initiative, right? So I didn't tell our studio to make the width of each of my columns, of my bins, to be exactly 10. Now there is a formula. Actually, what I didn't tell you is there is a formula which is called Sturges Formula that basically finds the optimal number of bins for the histogram to look nice and informative. Okay, so unless something else is specified, then my guess is that HIST function is using this Sturges formula. Okay, but what if I want to modify how the histogram looks? So instead of the bins, these intervals to be $10 each, I'm going to make it $15 each. So in other words, I'm going to have less bins, right? So now I have what, 120 divided by 10, that's 12, right? 12 bins. So if I'm going to make the width of each of my classes to be, instead of 10, 15, what's 120 divided by 15? That's going to be 8, right? So instead of 12, I'm going to have 8. So the histogram is going to be less detailed, so to speak. Can I do that? Well, turns out, yes, I can. So, and here's how I can do it. I can specify where the breaks should be. So my default breaks are, the first break is at 0, next one is 10, next one is 20. Instead of that, I'm going to make them to go with the interval of 15, right? So, and that is done. I know that because I did it before, breaks. So I'm going to specify one more parameter to the function. And breaks, because it tells the histogram where to put the next, the beginning of the next bin, and that's a number, and there's a bunch of them. That's going to be a vector, okay? Vector of numbers. And you remember how we create vectors, right? We use the function C, stands for combine, okay? So my lower boundary is going to be 0, next one is 15, then I'm going to have 30, oops, alright, 45, 60, next one is 75, 90, 105, and the last one is 120, okay? So let's go ahead and run this one, and there you go. So, and look at that. Now my 60 is not enough, right? So it cuts off at 60, so let me go ahead and change the range. I don't know, quite frankly, how high should I go? So how about 80? Yeah, 80 will do the trick, okay? Alright, so here's my new histogram, and you can see that it gives me basically same features, right? If you remember my previous histogram without any breaks, so let me go ahead and delete that one, show you the old form. Here's my old histogram, so I have a spike, a peak here, okay? Then I have a valley, then it starts to spike again, not quite as high as the first one, and then it kind of goes back down, right? And here's my new histogram. Shows me pretty much the same feature, right? First it starts off high, then it kind of has a valley, and then there is a second spike, and then it goes down again. So it's more, it's less detailed, of course, this histogram than the first one, right? But I still can probably extract pretty much same info. Okay, so we're kind of moving along this program, right, that we outlined for ourselves. Plot the data's histogram, we did that. Modify for the histogram, for the class width to be 15, we just did that. What information can we extract from this data? Well, let's discuss. So, if you remember, the idea was that, okay, here is the distribution of bills that our customers are paying. Can we do something about that? Can we steal some of our competitors' customers to switch over? Well, let's see. This one right here, so out of what, 200, right, 200 observations, 71 plus 37, that gives you 108, almost half, more than half actually, right? More than half are paying 0 to 15, 15 to 30, so 30 or less dollars, right, in their monthly bill. $30 as a monthly bill for the phone is not a lot of money, right? So therefore, since we're competing on the cost and we are going to offer people cheaper services, what is the chance that I'm going to call customers that have bills under $30 and tell them, hey, do you want to save what, $5 a month or $10 a month? What is the chance that they will buy it? And yeah, of course, that's a real deal, so I'm switching. Probably not a lot, right? So therefore, these customers we cannot entice with low prices, right? How about this three bars in the middle, 13, 9, and 10 out of 200? Well, first of all, because there is a value over here, right? That means that we don't have a lot of customers with mid-range prices, okay? So they're paying between 30 to, that is 75, right? But if you look at the high end, what do we have here? 18 plus 28 gives you 46, plus 14, that gives you 60. So 60 customers out of 200, that's roughly speaking 30%, right? So 30% of the customers are paying $75 and above, and that, quite frankly, is a lot for the phone bill, right? I don't know what they're doing. They may be using the long-range services, right? So they're making international calls or whatever, but to pay $75 or more for the phone service, that's pricey. So that is probably the group that we can try and contact and say, hey, if you're paying a lot of money, then come to us, switch from your current provider, and we're going to give you a break. You're gonna pay less. Okay, so this is what kind of info we can extract by looking at the picture. All right, so coming back to the to the slides, let's discuss briefly. So I actually pretty much put all these things that we have discussed right now on the slides. So, and I'm going to upload the slides to the lecture notes to Scholar right after I'm done recording this lecture. Okay, so and that's what we discussed last. Okay, so over 50% of the customers pay less than $30, so that's pretty much dead end. We're not going to go anywhere with these people. That mid-range, we could probably go after them, but there is not a lot of them. That's the problem. But 30% of customers are 75 or above, and that's probably our target audience, right? Okay, so let's briefly discuss also other things, other characteristics of the histograms that can be important. Well, first of all, symmetry. Okay, histograms are characterized with respect to the symmetry. So in this case, you have on this picture, you can see examples of symmetric histograms, right? Why is it symmetric? There is clearly a middle of the data distribution, and the left side is just a mere reflection of the right side. So that is called bell-shaped histogram, right? Kind of has a peak in the middle and it goes down on both sides. This type of distribution is called uniform because it's level at any value of the variable, has the same value, and that one is called bimodal. So we're going to discuss modality in a couple of slides, but modality basically is how many peaks the histogram has. Okay, so this is a unimodal histogram, right? Because there is only one peak. This is a bimodal histogram because there is peak 1 and peak 2. Okay, so symmetry. These are examples of symmetric histograms. Well, the majority of distributions in real life are not symmetric. This is an example of clearly asymmetric histogram, right? If the histogram is not symmetric, then we can talk about skew. Skew is a measure of asymmetry of the histogram. Skew can be positive, so this is a positively skewed histogram, and or skew can be negatively skewed histogram. And the way how you can tell is if you have a long tail going in the right or positive direction of the horizontal x-axis, then you have positively skewed. So it goes into the plus side of the x. Then it's positively or right skewed. If the long tail goes towards the minus side of the horizontal axis, then you have negatively skewed histogram. Well, a couple of examples. Right skewed histogram, very typically, probably classic example, distribution of salaries. Okay, if you look at distribution of salaries in any organization, you will see a lot of people that are being paid on the low end of the spectrum, and as you get to higher and higher and higher salaries, less and less and less people are paid big bucks. If you're interested, you can Google salaries at CNU. This is actually public info, maintained by I don't even remember, it's something in Richmond, and you will see that distribution of salaries at CNU follows exactly this this type of it's right skewed. Okay, another example that I always bring when it comes to skew is insurance. So when you drive the car, sooner or later probably will have accident, right? So there are a few people who didn't have any accidents in their life. The majority of accidents, thanks God, are very minor, such as fender bender or just light scratch, right? So they're low dollar value accidents. Okay, so therefore you have so if you horizontally here you have dollar value, right, of the claim, of the insurance claim. Then if you're here on the left side of the histogram, where you have, let's say, $100, $200, up to $500 collision. There are a lot of them, okay, very minor things. And as you get to more and more severe accidents, so for example, there is some damage to, I don't know, airbags deployed, right, or you need to fix the frame or something like that. So the more expensive it gets to fix and pay medical expenses or whatever, right, the less of these accidents, thank God, we have. Okay, so if you're talking about total loss with a lot of medical expenses, then there are only few accidents like that. Okay, so this can be distribution of insurance claims. How about negatively skewed? Negatively skewed, another good example, probably also comes from automotive industry. Amount of money that it costs to maintain your car. So versus time, for example. Okay, so as the car is getting older, the amount of money is getting higher and higher and higher. Okay, so it can be it can represent the distribution of amount of your repair bills as the vehicle gets older. When you have a brand new car, you don't need to do anything except maybe change oil every once in a while, right? But as you drive it more and more and more, at some point in time you have to, I don't know, flush the radiator, and then your timing belt needs replacement, and then you have to change the tires, and after that, God forbid, transmission goes out of commission, right? Or maybe engine breaks down. So therefore, these are expensive things to fix, but they don't happen typically until 10 years maybe into the life of your vehicle, right? Okay, so shapes of the histogram: symmetric versus skewed. Okay, then modality. That's another way how we can characterize the histograms, and we already saw, right, a couple of slides ago, we already saw this is a bimodal histogram. So mode is the most frequently observed value in the data, or in case of histogram, the tallest bar, right, the most frequently observed class or bin in the histogram. So this is an example of unimodal histogram. There is only one peak, and it's probably right skewed because it has a longer tail going to the right direction, right? And that is an example of the bimodal histogram. So there is one peak and another peak. So our distribution of phone bills from the previous example was bimodal, right? We had a peak, tall peak for the low values of the bills and the valley, and there is a smaller peak for high values of the bills. Okay, so number of modes or peaks, that's another characteristics. Histograms can be unimodal, bimodal, trimodal, multimodal distributions. Okay, and that's pretty much the last slide from this slide deck. So bell-shaped. So in a couple of lectures down the road, we're going to discuss something that's called normal distribution. Okay, normal distribution oftentimes is characterized to be bell-shaped. So bell-shaped is unimodal, symmetric, and it goes down pretty quickly to almost zero on both right side and left side. Now bell-shaped histograms, especially normal distribution, they play the important role in statistics. And why is that exactly? We're going to discuss in about a couple of lectures. Okay, but I just wanted to point out here that bell-shaped is a special type of distribution which is very popular in statistics. It's kind of a celebrity in the world of the statistical distributions. Okay, so that concludes this lecture, and in the next part, in the next one, we're going to discuss numerical descriptive measures. So in this chapter, we have in these couple of lectures we discussed graphical descriptive measures. So how can you put a picture on the data? So in the next lecture, we're going to discuss numerical descriptive measures. So how can you characterize a data set with just a handful of numbers that you can calculate from the data? All right.